We're now going into phase changes, and by definition, it's a transformation from one phase to another. Phase changes occur when energy or heat is added or removed, and a phase change is actually a physical change. The first one we're talking about is changing from a liquid to a vapor. In two terms, I want you to know them: evaporation and vaporization. Both mean the same thing. It's a process in which a liquid is turned into a gas. Evaporation is used when it's in an open container. Commonly, vaporization will occur when it's in a closed container. And that's going to make sense when we move on to vapor pressure, because in a closed container, as it changes to a liquid to a vapor, it builds up pressure, also called gas pressure. Now, the molecules within a liquid have varying amounts of kinetic energy. That means they're moving at different speeds. When the kinetic energy of a molecule is enough for it to escape from the liquid phase, it becomes a gas. So escape from liquid phase means it has to have enough energy to break the intermolecular forces. Now, evaporation can occur at any temperature, but as the temperature increases, the rate of evaporation will also increase. And this is because as the temperature of the liquid increases, so is the number of molecules with the minimum energy needed to escape or to change from a liquid to a gas. So again, as you increase energy, you increase your kinetic energy, you're moving faster, and you finally build up enough energy to break free from the liquid state and move on to the gaseous state. This diagram represents what we just talked about temperature and escaping from the liquid state to the gaseous state. Both these, again, number of molecules in the y-axis, and the x-axis you have kinetic energy. T1 is at low temperature, and T2 is same experiment but at a high temperature. The shaded area on both these are the minimum amount of molecules that have enough energy or enough kinetic energy to break the intermolecular forces and to change from a liquid to a gas. As we see, as stated in this, as we do increase the temperature, we increase the overall number of molecules that have enough kinetic energy to escape from a liquid to a gas by breaking the intermolecular forces. Key word in this next part is volatile, and by definition it means liquids have weak intermolecular forces, therefore they can evaporate easy. If you have a liquid that evaporates easy, changes from a liquid to a gas very easy, it's referred to as volatile. Now, key statement here, key understanding is that something that is volatile is flammable, because the state of matter that actually burns of anything is the gaseous state. So something that can change from a liquid to a gas very easily, produce a lot of gas, is also can burn very easily. A lot of your cleaning stuff, rubbing alcohol, acetone, gasoline, and you put them in your car, the gasoline, you know this one right away. As you fill your car up with liquid gasoline, you smell the gas vapor right away. And so those are what we call volatile liquids, and they're also flammable. You'll see if you buy anything at Lowe's cleaning supplies, you'll see the word flammable on it. It just means the liquid is volatile. Now, the more volatile, or which is more volatile, I was going to compare water and gasoline, makes sense. Which we're going to, again, which one can you actually light on fire? Gasoline. It wouldn't take much, put a little match up there, and it's going to light on fire very easily. So also, if you go back to intermolecular forces, because remember the could change from a liquid to a gas from its breaking intermolecular forces, we see that water has hydrogen bonds pretty strong. Gasoline is a true hydrocarbon, truly nonpolar. The only thing that holds nonpolar together is that of dispersion. Evaporation. I want you to know this key statement here. When you talk about evaporation, changing from a liquid to a liquid to a gaseous state, it's actually a cooling process, because what happens, the high energy on the area outskirts of the moisture, and those have a high energy or the high heat are the ones that have enough kinetic energy and they break free. So the heat leaves and they leave the cold behind. So this is a process of us sweating. Sweating is a cooling process for our bodies, and that the moisture on our bodies absorbs the heat from our bodies. The high energy or the hot molecules on the very surface of the sweat build up enough kinetic energy and they escape. They evaporate, change from a gas or liquid to a gas, and leave the cold behind. And that's how our bodies actually maintain themselves or maintain our body temperature. So sweating. So again, someone gets heat stroke too, is because they're not drinking enough liquid and they just are not able to sweat properly to get themselves to cool down. Vapor pressure. Now remember I talked about vaporization, and vaporization, this was when changes to a liquid to a gas in a closed container. So as it changes to a liquid to a gas, the more gas is formed, you build up pressure. We call that vapor pressure. It's also gas pressure. But as we have a closed container, it will reach an equilibrium in that it will change from a liquid to a gas going through evaporation, but it'll also start at the same rate be changing from a gas back to a liquid, which is condensation. So a closed container will reach equilibrium. As the temperature increases, taking on vapor pressure, if you look here on the chart on the right with water, as we increase the temperature, we increase our vapor pressure. As we get up to 100 degrees Celsius, we see that the vapor pressure of water is 760 millimeters mercury. I'm going to talk about that in a second. Or actually, I'll talk about it right now, because boiling point. When boiling point, or when a substance boils, is not due to temperature, it's due to pressure. For something to boil, its vapor pressure must be equal to the atmospheric pressure around it. So once those two equalize each other, boiling starts to occur. And boiling point, again, is going through a phase change, so it will maintain the temperature once your water starts to boil. But water has a vapor pressure at 760 millimeters mercury, which matches up with 1 atm, or 760 millimeters mercury in standard conditions. And this happens to occur at 100 degrees Celsius. So we just say boiling point of water is 100 degrees Celsius. However, I can change the boiling point of water if I can change the actual atmospheric pressure around it, and I can actually do that in a bell jar. Boiling is a form of evaporation. So just like evaporation is a cooling process, so is boiling. And if you don't have a heat source below the water to maintain the temperature and maintain the boiling, boiling will, as the water boils, the temperature will actually cool down. And I'll be able to show you that. But it's very, very important to understand that temperature, when water starts to boil, you're at a constant temperature. Remember, you're not going into a temperature change, you're strictly going into a phase change. To give you an example of this, our diagram, we have standard atmospheric pressure of 1 atm, or 760 millimeters mercury. The arrow going down is my atmospheric pressure. The arrow going up represents vapor pressure. If my atmospheric pressure is 760 millimeters mercury, water matches that with its vapor pressure of 760 at 100 degrees Celsius, and that's why we say water boils at 100 degrees Celsius. If, however, I would increase my atmospheric pressure up to 800, I would then have to increase my vapor pressure. To do that, I'd have to increase my temperature so I can get higher pressure and get water to boil at a higher temperature. However, the opposite of that, if my vapor pressure drops, or my atmospheric pressure, excuse me, drops to 240, my vapor pressure only has to get 240, and for water that can reach that a little over 70 degrees Celsius. So we see that, and that occurs on Mount Everest. Now, again, once your water starts to boil, it maintains that temperature. Now, answering some questions, it says, does it take more or less time to hard-boil an egg on Mount Everest at sea level? And the answer here around this one is, problem is, again, at sea level, water is going to start to boil at 100 degrees Celsius. On Mount Everest, it's going to boil at 70 degrees Celsius. So yes, Mount Everest, it will start to boil quicker, but you're not cooking at such a high temperature, so it'll take you longer to cook. Can you cook spaghetti if you faster? It's boiling and you turn up the flame when it's boiling already. No, you can't. Because remember, when it's going through a boiling, it's going through a phase change here. And that phase change is, all the energy is going to the phase change, not a temperature change. Now, you can get it to evaporate quicker if you want to, but all in all, it's going to maintain the same temperature. Next two questions, can you cook quicker with a lid on your pan? And you actually can. It will trap some of the heat, so you will cook things quicker. They even do it even quicker. A greater way to trap that heat and build up pressure is by way of using what we call a pressure cooker. And a pressure cooker, you literally a lid that locks onto place, and you can actually cause, again, the increase the pressure, therefore increase the actual boiling point of the water, change it to steam. The steam then cooks your vegetables, and you can cook your vegetables at a very high temperature and cook them quicker, therefore saving the nutrients. And it's a great way to cook your vegetables, because if you boil them quite often, when you boil vegetables, you actually destroy the nutrients in them. Critical temperature and pressure. There's key terms here. One is condensation. And condensation is the opposite of evaporation, and it's a substance can be made to liquefy by two different processes. As two ways we can do this, we can actually lower the temperature, which will decrease the kinetic energy. The molecules move slower, they get closer together, and then they change to a liquid. or we can increase the pressure and we can force them closer together, and as they get closer together, intermolecular forces take over and they bind together and they actually change back into a liquid. So the fact is just getting them closer enough together so the intermolecular forces can take over, whether you have them move slower or you push them together with increased pressure. Two other key terms I want you to understand are critical temperature and critical pressure, and they love to show up on the test. And so critical temperature is just saying above the critical temperature, a gas cannot be liquefied. A better way to say that is that this critical temperature is the maximum temperature which a liquid can exist as a liquid. A substance can exist as a liquid. Sorry about that. Now, above the critical temperature, molecules have too much kinetic energy, and therefore the intermolecular forces cannot hold them together. That's why they will no longer remain as a liquid, and they will change to a gaseous state. So they reach their maximum point, which they can be a liquid. As the strength of the intermolecular forces, though, increase, you can actually increase the critical temperature as well. Now, critical pressure, this is the minimum pressure that must be applied to bring about liquefaction at a critical temperature. Going from a liquid to a solid equilibrium, another key terms, you know these, freezing and melting point. Freezing point and melting point both occur at the same point, and for water that's 0 degrees Celsius. It just depends. If I'm getting warmer, I'm melting. If I'm getting colder, I am freezing. And so both of them occur at the same point. Freezing is changing from a solid to a liquid, whereas melting is changing from a solid back to a liquid. Now, jumping from a solid to a vapor or a vapor to a solid, I have another key terms, know them, sublimation and deposition. And a great example of this we see with dry ice. Sublimation is actually going from a solid to a gas, and that's why dry ice gives off a solid and it gives off that gaseous, the gases and the smoke, great for the Halloween effect, but it's bypassing that state of a liquid. And so it's literally jumping from a solid to a vapor, bypassing liquid, so we call it sublimation. Now the form dry ice, it's just gas, it's just carbon dioxide changed from a gas back to a solid, and they do that by the process of deposition.